Welcome to the first problem. Actually, this is take two of the first problem because I had trouble with the mathematics. I had trouble with handling the studio recording technology. And my English turned bad. So I decided make to make another go to try once again. So here's the first problem. I discovered something like that. Something like 1987, I think. I was very proud, and I wrote to the university, and they told me that that was a result that had been known for much more than 2,000 years. My God. Well, I'll try to make a better proof than I did then. So we have a prerequisite and a conclusion, and we actually have to prove that we can go backwards as well. So we assume 1 and we'll prove 2. No, it's the other way. We'll assume 2 and then prove 1. So we will assume we have 2 relatively prime integers, a bigger than b, bigger than naught, and then we shall prove that they form x, y, and z form a primitive Pythagorean triple. That they form a Pythagorean triple is elementary algebra. We'll skip that. So we need to show that they are primitive, which means they can't have a common factor. A and b are not both odd, and they're relatively prime, so they are neither even, both of them. So one is odd, one is even, what the academics prefer to call disparate parities. We'll just call them odd and even. So we have to show that x, y, and z cannot have a common prime. So we assume that they do. So this is odd, this is odd, this is even. So p is different from 2. And adding these two, we get p divides 2a squared. Subtracting that from that shows p divides 2b squared. So we get, since p cannot be 2, we have that p divides a and b, which is a contradiction. So this was the easy part. So let's assume 1. I've been through this before, so I know that we shall need the fact that x and y cannot both be odd. We'll just do that up here. We work modulo 4 in the residue classes by division with 4. There are 4 numbers. And the squares are 0, 1, and 0. So that means that the sum of two integers, x squared, y squared, can either be 0, 1, or 2. If it's 0, then we're adding two even numbers and the result is even. Won't do. So if we add two odd ones, the sum will become 2. That's not a square. So that means that x and y, one must be odd and the other even. So let's assume that x is the odd one and y even. You can see why I choose x and y like this. So the first idea is to subtract x squared on both sides. And factorize. This is a standard trick in number theory, classical number theory, that is. And then we assume that some prime divides y squared. And we shall prove that they cannot divide both. It cannot divide both factors. So assume p divides both factors. Now, z is odd and y is even, so both factors are odd. So p cannot be 2. That's a good one, that we can exclude 2 right away. So we add the 2. So p divides 2x and subtract them. P divides 2y. That means that it divides as well x as y. Therefore, we conclude that the prime can only divide one of the factors, and that means p squared divides the factor. So this means that this is a square, and z minus a is a square. Adding these give 2z equals, and subtraction gives, oh, I have goofed up. It was so nice to be able to discard the prime 2 that I don't get the right formula. So we'll have to go back and work with the two odd ones. So I think we can just think it through. Work it through. So now this is not nice. I have actually exchanged x for y in what we're doing. So that means that they are both odd, and that means that this is even. So 2 does divide this 2. So let's check the highest order of 2 that can divide these two. To what order can it divide both of them? Well, to the same order or higher, it divides 2x or 2y. But since one of those are odd, they're both odd, n equals 1. This is a little strange. If we take something like 8, 15, 17, then you'll see that, there's only 2 in between anyway when we take the 2 odd. It's not 8 between. All right. So maybe this is right. So it will actually have 2 as a factor as well. So we just delete them. Yeah. So this way we are through. I think that actually solves that problem. If not, you must write a comment. Now, I did get another idea the other day, so I'll just show it to you, and then we'll see if we can possibly solve the problem that way. And the reason for it was maybe we don't have a rectangular triangle. Maybe it's like 60 degrees. So instead of Pythagorean triples, we need triples satisfying this equation. So it would be nice to be able to make a parameter representation of the triples satisfying this equation. And the trick we just used won't do at all there. So I got another idea that might work. And the idea is to factorize the left-hand side. And then prove that a prime cannot occur in both of them and see what happens. Now we have to work in the Gaussian integers. The integers extended with square root minus 1. And it's a unique factorization domain. So we have units plus minus 1 plus minus square root minus 1. And all the primes come from the primes of z. 2 ramifies. It's actually 1 plus I squared. That's then divided by I or something like that. And the primes 3, 7, 11, they remain primes. And the primes 4n plus 1, they split. For instance, 5 equals 2 plus I times 2 minus I, which are 2 primes in this ring. So that's the algebra of the ring. So let's see what goes on by doing a simple example. So we have a factorization. All right. Now 5, that is this one squared. So that equals 2 plus I squared times 2 minus I squared. And if we compute this, it's 4 minus 1, quick, plus 4i. And this one is, of course, the conjugate one. So they turn out that this prime is this guy, and this prime, you can't see that, sorry. It turns out that this prime goes into this vector, and the conjugate goes into this vector. So it does seem as if we should be able to come through it with it. So assume P divides both of these guys, then it divides the sum and the difference, never mind the unit. And again, how many times can, that's 1 plus I, how many times can 1 plus I occur here? I claim it's twice. Oh, now I'm being silly, am I not? Because one is odd and the other is even. And all in this, in the ideal generated by this, they are either both even or both odd. So 2 cannot occur. Am I right there? It does not occur. Now let's do the academic term. And what is it called? Disparate, whatever. So another prime, if it divides both of them, it must divide x and y, both of them. So actually we have and then x minus iy must be the conjugate squared, because it's just the conjugate. So we write A as R plus IS. So that's 2x equals this one. Oh, minus S1. Minus S squared plus this imaginary guy. Then we add this one. That gives a factor 2 to it. And then the imaginary part is subtracted. I y. So it's only the imaginary part that's interesting, and that's 2IRS minus 2IRS. So this way we get x equals and y 2RS. Now, that was lovely. It was much easier than I had expected. So I like this better than the other one. The drawback, of course, is that we are basing all this on a result on well, what are we actually using here? This may be real, of course. Actually, we are not using this at all. We are not using this at all. So we are using two, aren't we? Yes, we are using something about two, but that's just an ideal. So there's no specific knowledge needed. So it's actually quite lovely. Well, what do you think about that?